what is a polynomial kernel. So this is the idea of a polynomial kernel. So you see people, talk about kernels, they use so much mathematics and, they, calculate so much stuff but ideally you do not require anything. This is so simple. You just project your one-dimensional data to a high-dimensional data. You square it. You just square the values and plot them in a high-dimensional data, see which is the line that is fitting in the best, right? I think, yeah, as I said, I will not do any complicated mathematics that was done in the lectures. So this is a way to, learn it simply. So anybody can understand. That's the point. Okay. So we just learned what is the idea of a polynomial kernel. So here are some of the kernel functions that you can use. For example, like you might have thought like, why did I just square it? Why not cube it, right? Why not take to the power of 4 or take to the power of 5 and so on, right? So you can do so much stuff. Why just, take polynomial? We can do other functions. We can like transform them with some, let's say, exponential or sine function, or we can take any function, right? Why just square it? So I think those are valid questions. You can do it actually. So for example, you see that for the polynomial kernel, so this is the kernel. So x1, x2 plus c whole to power t, right? So what you are doing here, in our case, what we just did is our d is basically 2, right? And c was 0, right? So basically this will just become uh, x1 times x2, right? So I will again come back to this, like how do I relate this kernel function to, uh, for example, to what we just did, right? So let me come back to the whiteboard again. So we saw the kernel function for polynomial is you know x1 times x2 plus c whole to the power t, right? So again, these are one point that I want to make before moving forward. So which value of C to choose, which value of D to choose, these are dependent on your data. You could choose, again, these are hyperparameters and you need to fix the value of C and D based on cross validation. So you can train your model based on different values of C and D, and finally, check which is which value of D is giving you the least cross validation error, and that is the uh, model that you should take. Okay. So just to explain what is the physical meaning of this kernel, right? So Kij would be, let's say, Xi Xj. So in this case, we have only one feature that is just let me see once. All right. Okay. Okay. So anyway, so in this case, our xi are the dosage value, right? So what is this physically doing? What is xi and xi times xj plus c whole to the d physically doing, right? So it is just creating. Uh, so okay, let me come back a little. So what is Kij? What is this kernel? Physically, what does it mean? So let's say you take this example as your ith example, the first one. This example as your ith example. And let's say this example as your uh, jth example. So based on this, you'll get some value, right? So if you see it's getting 1 times 6 plus c whole to the t, right? You'll get some value. Now, the question is, what does this value mean physically? Physically, it means that how closely related are these two features? How closely, sorry, the examples. How closely related are this one example and the six dosage, right? For very close examples, for example, 1 and 2, right? These are closely related, they are close to each other. You will have a lower kernel value, lower value of k. Whereas for 1 and 6, you will have a higher value of k. Is that clear? Okay. Okay. So that is what the kernel basically physically means. Okay. Okay. Someone has asked, Menak is asking to explain the last figure. So which figure? You mean the dosage, the two-dimensional transformation, or the kernel part? Both. Okay. Okay. So initially, what we had is this 1D data. You had dosage. Your black points are the points which are in which the medicines are not working. So black means y equals to 0, and the red points are the one y equals to 1. Okay. Now, using this data, you have no way to classify clearly. So earlier, what we used to do, we used to draw a line and say that okay, whatever is the left of the line, y equals to 0. Whatever is on the right, y equals to 1. But now here you have two additional points, 10 and 12, right? Which also have y equals to 0. So you cannot do this line thing, right? So what you do is you project your data into a higher dimension, two dimension. So one way to do is, just take the square. So for example, this is 1. You take the square, 1 square is 1. You plot the point in two dimension. Similarly, you plot all other points. This is a 2 comma 4. Okay. You take the second point, square it, plot it, right? Similarly, you plot the other points. Now in the two dimension, what you can do is you can draw this line, right? This line that you have drawn. And you can say that, okay, whatever is in the right of this line, it's classified as y equals to 1. Whatever is on the left of this line is classified as y equals to 0. That is the way you do it, right? So you're projecting it into a higher dimension data. But physically, you actually do not project it. What you do is you calculate this kernel function. This kernel function in the background is actually projecting it, but physically, you don't project your data. So the kernel function will just give you a value of uh, which is a measure of how uh, closely related are 2 points, right? So yeah, but to understand it, to understand how the kernel function performs, it's easy to visualize it in as a as a projection into a higher dimension, right? Is the explanation clear now? Is the explanation clear? Now, let me explain through an example, like how this kernel function does this. Okay. So let's say, you have this, let's say two values, okay, and two values of dosage. One is A, one is B, right? Now, uh, what will be the kernel value of this two? Let's, make this. Okay. So let's say you take A times B plus, let's say you fix your this thing C value to be, let's say 3, okay, for now. And you take the D value to be 2, okay, for this particular example. Now, what will the kernel value for these two examples? So if you just square it, it's simple, this square plus 6AB plus 9. Okay. Now you can write this as a dot product. Okay. Right. Let me see this. Okay. There should be some factor of root 6 over here. Yeah. So what is a dot product? So let's say if you have 2 points, x1, y1, and another point is x2, y2. So dot product between these two vectors, so if this can be represented as two vectors, right? So dot product between these two vectors would be x1, x2 plus y1, y2, right? This is what a dot product is. This is the dot product between two vectors. Similarly, if you like, this is your two vectors, right? This is one vector and this is another one, right? So dot product will be multiplying the corresponding values. So root 6a times root 6b, that will give you this term, and a square times b square will give you this term. 3 times 3 will give you this term, 9. Okay. So you can write this kernel. This kernel is just a value, right? Based on the value of a and b. Let's say a is 1 and b is 2. You can calculate the value of the kernel. This will just give you a number. This will just give you a number. But this number, the way to think about it is you can think about it like a dot product between two vectors, right? So as I said, what are the two vectors? The two vectors are root 6a square. Let's ignore this for now because both this is same in both the cases. 3 is same. So it can be represented as root 6 times a comma a square. So how do you use this kernel when you are uh, transforming your data into higher dimension? So what you will do, your x-axis would be root 6 times a. So earlier a was here. So let's say initially a was here, b was here. So next time when you are using this kernel, what you will do? You multiply a times root 6. You plot this into new position. This is your root 6a. Similarly, multiply root 6b. This is your new root 6b. And then you will also do a square. So let's say this is the a square. This distance is a square, right? So this is your new representation of a. Similarly, new representation of b would be root 6b comma b square. This is your new coordinate. Okay. New coordinates are root 6a square, root 6b b square. Right? This will be your new representation of your data in higher dimension. Right? Is that clear? So Prerna is asking x10 and x12 value would be larger, although they are close. Yeah. So you see, you can like calculate the value of x10 and x12, right? Wherever they lie using this formula. So, but not formula, but using this method, depending on whatever C you choose and whatever D you choose. In this case, if you're choosing 3 and 2 as C and D, so you can map. So if your x is 10, so it will be mapped to root 6 into 10, comma 10 square. So wherever the point is in the xy plane, 10 root 6 and 100, that's where your new projection of a in higher dimension would be. That's clear, right? But instead of actually projecting the data into higher dimension, you're just calculating the kernel. You're just calculating a value, calculating a number, which explains the relation between 2 points, in this case A and B, in higher dimension, right? Without even going into higher dimension, the kernel tells you what is the relation between the 2 points in higher dimension. That is such a powerful method. That's why This kernel method is so powerful. Okay. Now coming back to the slides. Okay. So I just explained what is a polynomial kernel, and linear kernel is just using as it is. It is just basically not using any kernel, equivalent to not using any kernel. So you're just not projecting it into a higher dimension. You're just keeping the dimension same. And Gaussian kernel, this is another way to uh, also called radial basis kernel. Another way to transform your data into higher dimension and check the relation between the two points in higher dimension. So you could, as I said, you could have any function. You not necessarily need to have a polynomial function. It could be a exponential function as well. And this is a sigmoid kernel, which is a tan h function, right? Hyperbolic tan function. You could have any kernel of your choice, right? But not necessarily all the kernels will give you better performance, right? So you have to see which kernel is giving you better performance and what are the parameters that you choose. Like in this case, you have to choose gamma parameter, which gamma is giving you better performance and so on. Like you have to see that, okay? But these are some of the examples of the commonly used kernels, right? We'll see a hands-on exercise on the usage of all these kernels, right, after this slide. So that will become more clear on how to uh, hyperparameter, how to tune the hyperparameters like C, D, gamma, and so on, right? So again, this is an example of let's say 2D data, right, on this thing, and the red points are let's say y equals to 0, green points are y equals to 1. So you can see a clear boundary could be a kind of a circular kind of a boundary, right? But in some cases, it might not be that obvious. In this case, it's obvious. So what you do is you use the Gaussian kernel and you project it into a higher dimension data. So now you see, okay, this set of points are clearly forming a different cluster. So in this case, it is just mixed together, right? You cannot have a straight line which is uh, separating the red with the green points. You cannot draw a line. But in this, when you're mapping it to a 3D data using any other dimension data using a kernel, you can see, okay, you can draw a hypersurface, hyperplane, like this decision surface that they have shown to clearly separate the red points and the green points. So this is how a projection actually looks like into a higher dimension, right? And then the hyperplane will become basically this circle. And then you can draw a circle in the 2D as well to see which is the best support vector classifier, right? Okay, so Priyank is asking why we ignored 3. Uh, where did we ignore 3 in the example? Mhm. Oh, acha, you mean this 3. Okay. Okay. So why we ignore 3 is that you might not ignore, I mean, you can take 3 as well, but you see, this will add another dimension to the data. So it will be a 3D data in which your z-axis value is 3. But since in both the cases, like both the vectors have same z value, so that means in the 3 dimensions, they both lie in the same plane, right? So so that's why you ignore 3. Yeah. But the question is like, yeah, like Priyanka is saying that if it was different, like in this case, if it was 3 and 2, then we cannot ignore. But since it is same in both the cases, we can ignore it. Right? Because as you see in the this will add a third dimension, and the third dimension value is same for both the vectors. So it is basically lying in the plane in the third dimension. That means it's just an 2D surface, right? Is that fine? You can just take 3 as well, but that will just, complicate the thing. Okay. Mainak is asking which one to use when. Suppose I have a tabular dataset which I have normalized. How to select which kernel I should take? Yeah. So Mainak, I will answer your question when we will do the hands-on. Again, there is no, you know, particular kernel that I can say that, okay, this kernel will perform the best. But yeah, let me show you an example hands-on, and then you can better